Okay, hello. We're now on the last topic for our course this summer. So we will be talking about DC circuits, so particularly the Kirchhoff's rule. There are cases that a given circuit cannot be reduced, okay, so using or by combining the given circuit into a series and parallel, especially whenever there are power sources or multiple power sources involved. Okay, so very often, so however, it's not possible to reduce the circuit to a single loop, so using these rules. So that is why the procedure for analyzing more complex circuits is made possible by using the following principles, which we are referring as the Kirchhoff's rules. So again, Kirchhoff's rules are used whenever a given circuit cannot be combined. So using either a combination of series or parallel combination of the resistors. So the first Kirchhoff's rule, so it's actually the Kirchhoff's current law. So it follows a junction rule. So that means at any junction, the sum of the currents must be equal to 0. As we have mentioned before, so current will be split whenever there are branches that are involved. So for example, on this given figure, so we have a branch. So in this case, so I1 is splitted into 2 as I2 and I3. Okay, so in identifying or in writing, okay, or in writing the equation, so we follow the Kirchhoff's law. So that is anything that is entering a point, okay, or a junction, so that is considered as positive, and then anything that is leaving the junction is considered as a negative. So in this case, as you can see, so we have this junction. So I1 is entering that junction, so therefore that is considered as positive. And then I2 is leaving the junction together with I3. So that is why, so our resulting equation then, so will be I1, so minus I2 minus I3. Okay, so that is for the Kirchhoff's current law. So Kirchhoff's current law is always used, okay, so in finding the current at a given branch. So while the Kirchhoff voltage law is used for a given loop, okay, so when we say loop, so we start on a given component or an element, and then we end with that element as well, or before that element. So that means the summation of the voltage across a given loop, so that will be equal to 0. So we have to make sure that we have a single loop, okay, so for us to perform the Kirchhoff's voltage law. Okay, so Kirchhoff's voltage law is used so within a single loop. So how do we find, okay, so how do we find the voltage drop, okay, so on a given element? Okay, so there are two ways or there are two voltage, or there is one voltage drop, so which is the voltage drop across a given resistor. In this case, whenever, let's say for example, if I'm going to find the voltage across point A and B, okay, so from point A and B, and then I have designated the current to be moving to the right. Okay, so if it is moving to the right, and then I'm going to have my loop, okay, so from A to B, as long as it is along, okay, so our movement is along the direction of the current, then that is considered as a negative. In this case, that is negative IR. So that is, I'm finding the voltage drop, so from A to B. So from A to B, so the current, okay, is the direction of the current is along the direction from A to B. That makes it negative. However, if the current is going to the left, and then I'm still finding the voltage drop from A to B, as you can see here, so from A to B is going to the right while the current is going to the left. So if the direction is opposite, then that is considered as a positive voltage drop. And then for a given source, Okay, so an electromotive source, we have to take note of the sign. Okay, so for example, so from A to B, so the direction is going to the right. So for a given source, we follow the sign of the leaving sign. So for example, from negative to positive, okay, so from negative to positive, so therefore that would be a positive voltage. But if we have, so let's say, a positive and then a negative, so if we find the voltage drop AB, or that's the voltage across the across the battery, so since it is going from A to B, and then it goes out from negative, then that makes it a negative EMF. Okay, so that's how we use the Kirchhoff's voltage law. Okay, so the voltage drop, so we have to take note of the direction of the current. So if it is along the direction of the current, so that means that is negative. If it is opposite the direction of the current, that is positive. But for power sources, if it goes out on a positive terminal, then that makes it a positive voltage. If it goes out on a negative terminal, then that makes it as a negative voltage. So let's have an example here. The direction of the current, okay, so the direction of the current is just an assumption. There are times that we will be able to get a negative current, so that means that our assumption is on the opposite direction if we got a negative value for the current. For example, in this case, so we have a single loop, and then we are to find the current in the given circuit. So since we have a single loop, that means there's only one current, so within the loop. So if I'm going to use the KVL, since there's a single loop and then I want to find the current, so I'm going to use this movement. So that is loop number 1, and then my direction is clockwise. So since my direction is clockwise, so that means my current, okay, so this is current I. So since the flow is going to the right, so therefore, in this case, this would be the flow of the current I. So on the volt on resistor, on the 8 ohm resistor, and then the same as true. So this would be the direction of I. So that there would be a continuous flow of the current. Okay. So there should only be one flow for the current here. Okay. So it goes clockwise. Okay, so for the current. So if we are going to find the value of the current, so we can use the KVL. Okay, so for the given loop. So in this case, so I'll just start with the E1. So for E1, so since my loop is clockwise, so that means so I'll enter at the negative terminal and then I'll exit at the positive terminal. So that makes it positive E1. And then, so for R1, so we have 8 ohms, and then the current is I. So the voltage drop would be I times R. Okay, so that would be, so since this time, so clockwise, our direction is clockwise. So therefore, so if that is clockwise, so this would be the direction of my loop. So this is along, okay, so with my current I, so therefore that would make it a negative I R1. And then this is my loop. So it goes out, it enters at the positive terminal, and then it goes out at the negative terminal, so that makes it negative E1. And then lastly, so for my R2, so this is the direction of my loop, and then the direction of my loop is the same as the direction of the current, so that makes it negative I times R2 as well, is equal to 0. So I started with E1 and then I ended up with R2. Okay, so I have to go through all of the elements involved in the circuit. So we are to find what's the value of I. So therefore, I can combine. So E1, I think this is E2. So minus E2 is equals to, so transpose I R1 minus or plus I R2. And then I can factor out I. So that makes it R1 plus R2. So thus I is equals to E1 minus E2 over R1 plus R2. And that is E1 is 6 volts minus E2 is 12 volts. R1 is 8 ohms and then plus 10 ohms. So that makes it negative 6 all over 18. So negative 6 divided with 18, that is 1/3. Or the answer would be negative, so we could have a 333.33 milliampere. And that would be our current. So the current is negative. Okay, so that means our assumption, the direction of our current is just the opposite. Okay, it's not from left to right. So if we want to make that positive, so we need to change our current so to be moving from right to the left. Okay, so regardless whether the current is positive or negative, it doesn't matter. So that only tells us that the direction, if we have a negative value for the current, so that means the direction is just the opposite of our assumption. Okay? So that is for example number 1. Then for example number 2, so we are to find the currents I1, I2, and I3. So in this case, there are 3 unknowns. So there are 3 current. So that is I1, I2, and I3. So in algebra, so whenever there are 3 unknowns, so we need 3 equations. So for us to find the 3 unknowns. But take note that whenever we are creating our equations, okay, so we cannot use KVL for 3 times. Okay, although that would be possible. Okay, so let's say I would have loop number 1 and I would have loop number 2. Then it would be possible that I have this loop number 3. But then if you're going to use that, okay, so if you're going to use 3 KVLs, so later on you will get a 0 for the value. So that is why whenever you are finding, okay, so whenever you are finding, let's say in this case, so 3 currents, so we should be using a combination of KVL and KCL. So in this case, what I'm going to do is, I'm just going to use 2 KVLs for loop number 1 and loop number 2. And then I'm just going to use a KCL. So KCL at this given point. So as to find the 3 equations. So we just have to take note of the flow of the current. Okay, so for our first branch, so if this is I2, so therefore this is the same current that flows here. So this is the flow of the current as well. So this is I2. Okay, so it flows, okay, so from B to E, from E to F, and then F to C. But then for our I1, our assumption is it flows from B to C. And then our I3, so it flows from C to D, and then D to A, and of course A to B. So this is the same as the I3. So now, so let's write our equations. So for our equations here, so I'm going to perform KCL at point C. So at point C, as I can see here, so I1 is entering. Okay, point C, I2 is entering as well, while I3 is leaving. So therefore, I can write that I1 plus I2 will be positive, and then minus I3, so which is leaving, would be equal to 0. And this would be my equation number 1. And then for my equation number 2, I can apply KVL for loop 1. So I'll start with the 14 volts. Okay, so if my loop is clockwise, and then it goes in at the positive terminal, and then it goes out at the negative terminal, so that makes it negative 14 volts. So I'll start with this one. Okay, and then next would be the 6 ohms or the 6 ohm resistor. So my loop is going in this direction, so which is opposite the direction of the current, so which is I1. So therefore, that would become a positive. Okay, so that would be plus 6 I1. And then it goes through as well. So from positive to negative, so it goes out at the negative terminal, so that makes it negative 10 volts. And then, so lastly, so this would be the direction of my loop. So this time, so it is along. Okay, so my loop is along the direction of the current. So if it is along, so that will be negative. So negative 4I2 is equals to 0. So this time, I'm just going to arrange it so that later on, I'm just going to use a calculator. So I'll start with 6I1, then minus 4I2. The negative 14 minus 10 is negative 24. And then I'm just going to transpose it to the right side. That would make it 24. And that is equation number 2. And then for KVL for loop 2. For loop 2, I'll start with the 10 volts. So it goes out at the positive terminal, so clockwise for my loop. So negative to positive, so that would be 10 volts. 10 positive. And then my loop is going to this direction, so which is along the I1. So thus it would become minus 6I1. And then so the loop is clockwise, so it is along, so therefore that will become 2I3. Okay, so 2, so it is along, so it should be minus 2I3 is equals to 0. Okay, so we have positive 10, then minus 6I1, and then minus 6I3. So which is equal to 0. And then, so I could rearrange this, so negative 6I1 and minus 2I3 is equals to negative 10. So that would be equation number 3. So I can now use my calculator. So since I have 3 equations, so you can use your mode 5. I think it's mode 5-3 if I'm not mistaken. So for my equation number 1, so that would be I1, I2, I3, and the voltage source. So we have I1, so we write the coefficient, so which is 1. I2 is positive 1, so I3 is negative 1. And then we have 0 for the D. So for equation number 2, so we have 6I1. And then we have negative 4I2. And then 0 for I3, but then we have 24 for then we have negative 6 I1, 0 for I2, and then negative 2 for I3, and negative 10 for I4, or for the source. So thus, we have then as I1, so to be 2 amperes. So I2 is 3 amperes, and I3, so it's negative 3, it's negative 1 ampere. So that only means that the direction will be, so we have a wrong direction for I2 and I3. So I2 should be on the opposite side. So this should be I2, and then this should be I3. So that's if we're going to consider that, so using KCL, so entering is I1 and I3. That means I1 plus I3 is equals to I2. So you can see here, I1 and I3. So just try to make the sign to be positive. So I1 is 2 ampere, I3 is 1 ampere. So once you added that, so you'll get the I2, which is 3 amperes. So you could have a negative current, but then the assumption is just the opposite one. So let's have our third and final example. So in this case, there's no assumption for the current. So I'm just going to assume. Let's say this is my assumption for I1, assumption for I2, and assumption for I3. The direction is just an assumption. So you can use whatever would be the direction that you want. So again, so we are to find the current in each resistor, and then you will be finding, so what would be the potential from C to F. So again, so we can write, or we can do our KCL at point F. So that would be a point F. So since I1 is going upward, so therefore this would be the direction of I1 as well. So this branch, okay, so from F to A to B, and B to C, that current would be I1. And then the current that flows from C to F is I2. And then so from E to D and D to F, so that is I3. So the direction of the current is, so this would be I3 as well. So KCL at point F, so that means I1 is leaving. So I'll have a negative I1. I2 is entering, so positive I2. And then I3 is leaving, so I'll have negative I3 is equals to 0. So I1 is leaving point F, so that makes it negative. I2 is entering point F, so that is positive. And then I3 is leaving point F, so that makes it negative I3. So that would be equal to 0, and that is my equation number 1. And then I'll have my loop 1, and then this would be my loop 2. So I'll do KVL at loop 1. So I'll start with the EMF. So E1, so this is positive, this is negative, positive, negative, positive, negative. So the loop, so it's clockwise. So it enters the negative terminal and then exited the positive terminal, so that makes it positive 70. So for this one. And then for this, so we have it enters at the positive and it leaves at the negative, so negative 60. And then for R2, so it's along with I2, so therefore that would be minus 3k times I2. And then for I1, so this would be my loop, so that would make it a negative, so it's along, so negative 2k I1 is equals to 0. Or, so we arrange this, so I'll have negative 2k I1 minus 3k I2, and is equals to 70 minus 60 is negative, or it's positive 10, and then negative 10. So for my equation number 2. And then lastly, so I could have the KVL at loop 2. The KVL for the loop 2. So I'll start with the 3K. So this is my loop. So my loop is this. So 3 is opposite I2. Okay, so the direction of my loop is opposite I2. So therefore that would become positive 3K I2. So 3K I2. And then it enters the negative terminal of the 60 volts, exited at positive terminal. So that makes it plus 60. And then R3, the loop is opposite the direction of I3. So that makes it positive 4K I3. Next, so we have the 80 volts. So it enters at the positive terminal and then it leaves at the negative terminal. That makes it negative 80. We have 1, 2, 3, 4. 1, 2, 3, 4. Okay. So that will be equal to 0. So I'm just going to arrange it. So 3K I2. So plus 4K I3 is equals to. So 60 minus 80 is negative 20. So I'm going to transpose it. So that makes it positive 20. And those are the three equations that we have. And then, so we just encode. Okay, so negative 1 for I1. So using equation number 1, positive I2 and then negative I3. So we have 0 for the voltage there, or 0 for D. Then we have I1, so negative 2K. So negative 2K is 2000 I1, and then negative 3K for I2, so negative 3000. So we don't have I3, then we have negative 10. For the third equation, so we have 3K for, or 0 for I1, and then 3000 for I2, and 4000 for I3, and then 20 for the constant. So that makes I1, so to be, we're gonna use, okay, so this is around 384.62 microampere. So I2 is, so 3.08 milliampere. And then I3 is 2.69 milliampere. So we're in, if you add I1 and I3, so that we will get I2. So which is true for these. Okay, so if we add I1 and I3, that would be equal to I2. So 2.69 milliampere plus 384.62 microampere is equals to 3.08 milliampere. So that is for the three currents. So next is we are to find the voltage from C to F. So for the voltage, so from C to F, okay, so that means, so I'm going to start. Okay, so my I2, remember that this would be the direction of my I2. But then, so we are to find, so the voltage from C to F. So that means this would be the direction of my loop. So therefore, VCF then will be equal to, so it enters the positive and then it leaves the negative, so that makes it negative 60. Oh, by the way, I think my, okay, so my current's going downward. So the current is going downward. So this is I2. And then, so this would be my loop. So since I am to find the voltage from C to F, so that makes it negative 60. So the voltage from C to F, that is negative 60. Then minus 3K I2. So since it's along the same direction, negative 3K I2. So negative 60 minus 3K. So I2 is 3.08 milliampere. So therefore, our VCF then, so will be, so negative 60, so minus 3,000, so times 3.08 expansion negative 3. So that gives us a negative 69.24 volts for the voltage VCF. And that will be all. Good day.